In today's lecture, we will be going over Jordan-Null set. So we are given the following problem. Let psi subset of R be a Jordan-Null set. Show that psi times psi subset of R squared is also a Jordan-Null set. Once we have shown this, we want to prove that psi times the closed interval between 1 and 0 subset R is also Jordan-Null. So we will just start by showing that psi times psi subset of R squared is also Jordan-Null. So by definition of the problem, we know that psi is a Jordan-Null set. And now, to prove the following, we will just fix some epsilon bigger than 0. And since psi is Jordan-Null set, we know that there exists an I, which is a finite cover, of psi. So we know by definition that the following inequality holds. We have that psi, the subset of the union of I equal 1 up to n, II, which is just all the covers, union, and psi's a subset of this entire cover. But we also know that this holds with the following proposition, that the sum of I equals 1 up to n of the vol of II is less than epsilon. This right here is just the definition of Jordan-Null. There's nothing special about here. We didn't do anything. We just wrote down the definition so we can work with this and prove our result. So since II is a finite cover, we can just write that psi times psi, which is just the standard Cartesian product, as we will just define some mu of II times Ij, which are just two covers, are defined as II, this is a big II, times Ij. This is just something I would recommend that you know, that you can rewrite this right here like the standard Cartesian product as the following right here. It's pretty nice for some proofs like this proof right here that we are doing with the Jordan-Null set. So we can write the entire measure. So we have like a psi and cross psi. So we have like, we can think of it like we have two, let's say, areas, and we want to cover this area with a finite cover. So let's assume we have all of this and we want to go over all of them. What we want to do, we have this one right here and we want to sum over all of them, or the cover of all of this is just like the iteration of all of them. I have the iteration of all of them, and this one right here. So this is basically what we have. So we have a double sum. We have the sum over the elements here, and we sum this over the following right here. This is quite important so we can write the volume of our cover itself, because we have two covers. So if I equal 1 up to L times J equal 1 up to L of mu of II times Ij. So this double sum right here is basically the representation right here. We want to sum over all the products. This is just what we are doing. And by the inequality right here, or basically because we have this property right here, we can rewrite this as the following right here. We know that this is less or equal than the sum of I equals 1 up to L we have the sum of j equal 1 up to L of mu of I times mu of ij, and this is equal to the sum of I equals 1 up to L of mu I times the sum from j equals 1 up to L from mu ij is less than epsilon squared. Where does this come from? This epsilon squared especially. We know by definition that psi is Jordan null, and if we go back up, that's why we wrote down the definition, we know that the volume of everything, when it's Jordan null, is less than epsilon. But don't forget, we just split the Cartesian products of our covers into two separate covers. So this is less than epsilon, and this part right here is less than epsilon. So the product of epsilon and epsilon is epsilon squared, and we know now by definition that psi times psi is also Jordan null. The last part right here, the part right here, we just split the sum up into its different components. This is justified due to the distributivity of the multiplication over the addition. So everything works fine, we didn't do anything illegal. But last but not least, the most important stuff, the rewarding stuff when doing math is, you just do the little box or the QED or whatever you want. I prefer the box. So we have now proven that when we have psi subset of R, a Jordan null set, that psi times psi subset of R squared, that this is also Jordan null. But for now, we have the other example. We have the example psi, let's write down x2 we now want to show that psi times 0, 1 is also Jordan null. It may not be Jordan null, it may be Jordan null, we don't know it yet, but we just want to prove it. Well, of course, we just assume that psi is once again Jordan null, but the problem right here is that 0, 1 is not Jordan null, because the smallest covering of 0, 1 has length 1. And if we choose epsilon to be 0.5, there's no way that 1 will be less than 0.5. 0.5 is just smaller than 1. So we have a problem. We know that this part right here is not Jordan null, but it may be. First of all, so right now we are not sure if this is Jordan null or not. What I like to do is I want some easy case to draw so I can decide which path I take. Usually I prefer, when I have a drawing and my assumption is yes, it is Jordan null, that I will try to prove that it's Jordan null directly. And if I have a drawing, a simple drawing, and I don't think that it's Jordan null, I want to prove the other thing. So for now, we will just assume that psi is just the natural numbers. So we have the natural numbers times 0, 1. This can be also drawn as the following right here. We have a graph. 1, we have the 0 here, and we have 1, 2, 3, 4, and 5. So n are the natural numbers, 1, 2, 3, 4, 5, etc. And we have 1 and 0. We can think of it as we take some natural numbers and then we just take a straight line from 0 to 1. So this right here is just we have our natural number and then we extend it into this plane right here, where every point in the interval 0, 1 is being occupied. So if you want the drawing of this, it basically looks like this. We have a drawing here, we have just a straight line here, we have a straight line here, we have a straight line here, we have a straight line here. All of them are just going from 0 to 1. So Jordan null is like a way to cover things. Really think of it like we want to put a blanket over this, and our goal is to show that something is Jordan null, then this blanket can be made arbitrarily small. My first guess is, since the height is always 1. Like, the height is always 1. But this part right here in the x direction, if this is the x, in the x direction, we have an infinitesimal element. So its width is basically 0. So the area would be given like height times base, and if the base is 0, everything would be 0. So my assumption is that the following right here is Jordan null. So we will just assume that this here is Jordan null. It's just for intuition. We want some idea what it could be. We don't know for sure. The proof may result in that it's not Jordan null, but it's just an assumption from our side that it may be Jordan null. But now I think we have talked enough. Now we just want to go into the proof itself. So first of all, for psi, we know that there exists a finite cover II of psi, just by definition of psi, because psi is Jordan null. So fix some epsilon bigger than 0. We will now once again define our Cartesian product. We will just take mu again, which is II times the interval 0, 1 is defined as II times 0, 1. Yes, that's just the definition of the Cartesian product. So now we can go over this proof a bit faster, or no, try to prove it yourself. So pause this video, try to prove it by yourself, because you will only learn math by doing math yourself. Just watching a video doesn't help. Once you've proven it, you can come back. If you are stuck somewhere, come to the video again, watch me, and if you think, okay, from now on I could probably try to show that it's Jordan null, you will try it again, one by yourself. So don't be afraid to pause the video, or maybe watch a sequence again, so you are sure you get everything that we wrote down. But for now, we have some I equal 1 up to L of mu I is less than epsilon. This is just like the length of the cover is less than epsilon due to its definition. If something is Jordan null, then the sum of all lengths is less than some epsilon. So this implies that mu in of psi is equal to mu out, which is just 0. This right here isn't that important. We didn't use it before. It's just good to know that when something's Jordan null, we have that mu in is the same as mu out. If you don't know what mu in and mu out is, you can go to the internet, or I will just make a separate video explaining the part right here. If you know it, it's nice. If you don't know it, it doesn't really matter. You can still prove everything. So to the proof itself. So we have the sum of I equal 1 up to L of mu of I cross 0, 1. And this is less or equal. You can think of it right here as we just take some element in this interval. So if we take the biggest the biggest element in this interval right here, we will for sure be bigger than if we take any other element. So the biggest element right here is 1. So we can rewrite everything right here as the sum of I equal 1 up to L of mu I times 1. This is the definition. Before we had like this definition right here. But for now we just like got rid of this interval because usually intervals are nice to work with. But if we just take the maximum or the supremum of the interval and we plug it in our formula right here, we know we will always, or this part right here, will always be smaller, because if we take something like 0.2, everything would be scaled down by 0.2. And this is by definition, because this part right here is just like the psi. And this is the interval right here, the 0, 1. But from the definition of Jordan null right here, from right here, we know that this is less than epsilon. That's just the definition of Jordan null. So we are less than epsilon. Hence, we have now shown that psi times 0, 1 is Jordan null. Once again, the most important thing is the box or your QED or whatever. If we step back a little bit, you may have noticed that we really just work extremely close with the definition. So if you are given some information for a proof, please try to use the information. Usually they don't give you information about something that you don't need. Don't try to prove this without using this property right here. If we give you that your psi is Jordan measurable, just write down the definition, because it really helps. You have like the definition, or if you're in an exam, just writing down the definition may get you some points. And if you write down the definition and you start with the proof right here, you may be able to see something that you otherwise wouldn't see. So please, 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 if you take real analysis, just stick with the definitions. Learn those definitions by heart and look how you can really apply them. Jordan null isn't that hard if you really try to wrap your head around it, but you really need time to digest everything and to really understand what everything means. But my tip, if you don't have the time, just learn the definition, write out the definition on your exam. Otherwise, just write some gibberish. Usually, the people that are correcting it are nice people, so they will just give you some points for the effort, and that's what you want. You just want points. You don't, if you are in the situation where you know you can't do the proof, just try to get some extra points. But now I have a question for you. We have now shown that this right here is not Jordan null. So let's assume that we have some A, which is also not Jordan null, and psi is Jordan null. Can we always say that psi times A is Jordan null? This is not an example that we will go over in this lecture, but this is a question for you. Think about it. Can you maybe come up with a proof or even a counterexample? This is something that I give you as homework. If you have a counterexample or even a proof, let me know down in the comments. I hope you really enjoyed this video. If you liked it, don't forget to like and subscribe. And until next time, good learning.